A lot of times with functions, it's a good idea to look at the function and say, before I take the derivative, could I clean it up a little bit? And it turns out that makes this one a ton easier. So here I could rewrite this function as the tangent would be sine over cosine. And the secant would be 1 over cosine. To clean this beauty up, I could multiply top and bottom by cosine of x, or I could view division as multiplying by the reciprocal. Either way, I'll take the multiply by the reciprocal route. And you see the beautiful thing that happens next?
Cancel.
Yeah, it turns out tangent over secant is really just the sine of x. So my f of x is really just 5x squared times the sine of x.
Oh, that's so much easier.
And then taking the derivative of that is way easier. So since we started it, let's finish it. The derivative with respect to x of that just involves the product rule instead of the product rule and the quotient rule at once. But that was a good lesson in applying both rules together. So I'll take the derivative of 5x squared first, which would be 10x. Sine chills out for a moment. Then 5x squared chills out for a moment. And I take the derivative of the sine of x. And I'm done. That right there is f prime of x. So I had to do the algebra up front, which meant way less algebra later. Okay, so if you can clean up a function before you take its derivative, do so. So it's always worth pausing to think about that. Apparently I was too excited to think about it yesterday, and I just dove into it. So be careful about just diving in. So it took us, what, 2 or 3 boards to do it yesterday, and this one took us, 1?
Less than 1.
Yeah, kind of less than 1. All right, so number 5 from the homework. I believe the version I had a minute ago was f of x equals 3x times the sine of x times the cosine of x.
And the answer the computer wanted was ridiculously long. Like, it didn't want you to simplify it all.
Usually it'll take multiple answers that are equivalent. So I did notice that some of the problems said, just leave this unsimplified version. Usually I want you to try and simplify it a little bit. So the computer system accepts more variations than I would accept in person. So here we have the product rule, but multiple times, okay? And it's actually not that bad. If I just kind of break it out, suppose we have function f times function g times function h, right? 3 functions, and we're taking the derivative prime. What you can think about is kind of saying those 2 are just really one function. So then what you get, according to the product rule, is you get the derivative of f times g times h plus f times g times h prime, right? Take the derivative of one, hold the other, then switch. But I better deal with that, which is the product rule again. So just that part right there would be f prime times g plus f times g prime. And all of that has to be multiplied by h, right? Mm-hmm. So I just sneak an h in there, h, f, g, h prime. And what do you notice about that new thing?
It just moves across.
Yeah, the same rule applies, which is take the derivative of one function, leave the other stuff alone. Then move on to the next function, leave the other things alone. So basically, one function gets the derivative at a time. The other things just hang out, and you just keep adding those up. So even if there were 4 things multiplied out, it's not that bad. Does that make sense?
Mm-hmm.
Okay. Yeah, so let's do it. And there's another way to do this one if you apply some clever trig identities, and maybe we'll try that version later today. So I'm just going to say, well, f prime, the derivative has to be the derivative of 3x, which is 3, and then sine and cosine have to chill for a minute. And then I'm going to add on to that, the 3x chills, derivative of sine is cosine, and that other cosine has to chill for a minute. And the first two functions chill, and the last one finally gets its turn. Careful with the SIGN, because we want to indicate that as multiplication by a negative, not a subtraction, right? So I got to have the parentheses there. Does it clean up much?
You do cosine
Isn't
squared.
inverse-
Times cosine
Inside inverse cosine C sine negative sine.
There's no inverse trig
Not,
functions
sorry,
here.
not inverse. The derivative of cosine is negative sine, not negative cosine. Like you wrote on the last page.
Well, thanks
oh,
to
crap.
negative cosine.
Yeah, I screwed that up. Derivative of cosine is negative sine. Thank you. Wow, this is strange.
I don't know why people do inverse. I'm because
Yeah, there we go. So let's see, what do we get there? We get, yeah, there's not a lot of like terms. Oh, there's kind of a like term there, I guess, right? All right, so the 3 sine cosine is kind of stuck. And then we've got the 3x factors out of those two, leaving cosine squared of x minus sine squared of x.
And when I tried to put that in the computer, it yelled at me.
Oh yeah, I didn't like that.
It made me write it all out. It made me
Oh.
write cosine times cosine minus
It made you just write this the way it
minus
is?
sine.
Mine just won't.
No, I was able to factor out the 3x, but that was it. Like that was
Yeah.
all the.
Yeah, this, I was hoping this reduced, but this isn't 1 because it's a minus, not a plus. Right. Ben, what?
Well, mine it had factored out the 3 out of everything, but then it factored out the x out of that one spot, kind of like it is. It just took the factor 3 out of everything like you have there.
So we could write it as 3 times sine of x, cosine of x, and then take the x out of the next ones,
Well, it's already out, but yeah.
plus x
That's how it's
cosine squared of x minus sine squared of x.
That's how the answer looks like.
That's how the answer looks. Okay, let's take a peek at what the online system has. Yeah, so there's a bunch of variations. I'm not sure one is any better than the other now. Except, does anybody recognize this thing right here? Oops, colors.
It equals 1.
That's not, if it was a plus, it would be 1.
Trig function.
What do you think? Say it again.
It's a trig function.
It is there is an identity for that.
Constituents something?
It is the cosine of 2x.
Oh.
It's the
Okay,
double
so-
angle.
Double.
Yeah. I don't know if that makes it any better. I don't know if this system will complain about that. Trig functions are tough because their identities really give you variations. So that was 5. Let's throw a 5x, no big deal. So I'm going to try it as my first version. So 5, I'll write it in the same order, sine of, trouble typing, x, there we go. The sine of x plus 5x, and I could say sine squared, and it might not like that notation. Sometimes computers freak out about that, and I'll talk about that in a minute. Minus 5x cosine squared of x. So that is one, ooh, that's not the right. That is one possible
Weren't
answer.
the signs negative, not the cosines?
No, because the, oh shit.
Yeah, could be
Yeah, that
parentheses.
would've
Oh, yeah, because the derivative of cosine is sine, so that should be a plus. You are correct, and this should be a minus. Yep, thank you. Derivative of cosine is negative sine. Okay, so let's see if it likes that. Ooh, it liked that. Interesting. Okay, so let's try variation on that.
I
What?
wonder if it,
Wait,
like,
can you just do the
gives
show
background
the
why
answer?
Oh, it's
so that
going to
they
show
have-
answer. Well, just because they have shown an answer doesn't mean that's the only answer.
Well, yeah, I know. I just wonder what their answer is.
They factored out the 5 and the x, and they didn't write it as squares.
But
So what the computer has a way of kind of evaluating to check if two different looking answers are actually the same, and it runs through that to check. And so it said, yeah, mine's close enough to this one right here. So there are going to be variations on those. Just a note on sometimes in some algebra systems, certain systems freak out about putting a square there. And instead, in some systems, what you have to do is wrap the whole thing in parentheses and then square it. Like that. Without doing any parentheses. Sine times sine, cosine times cosine.
No, the
Cosine
square
to
root,
the
the
caret square.
the second power right after the x without parentheses.
Oh, right here.
No, after the x.
no,
Like
just-
if you
like
wrote
you just-
cosine
And
x.
you don't have to put it in the parentheses.
Cosine
The whole thing in
parentheses
parentheses.
x.
No,
No,
like
no,
cosine
and
parentheses
square.
x.
Parentheses x.
X.
parentheses.
And
Square,
then
square.
squared.
Oh, no, that's horrible. Yeah.
It means
Oh, I
like
don't-
taking the square of the x, not.
Well, no, to square the x, it would have to be inside, but that's just bizarre notation. Oh, I don't like that. Yeah, just because we can write something doesn't mean it should be legal.
Just because you.
You only have so much freedom of
If we
speech.
put that on
Okay.
the test, will we get it wrong?
I would put a frowny face on your paper for sure. I'd prefer that.
I'll just put one just to get one.
Yeah. Okay, let's do something else. So leave, yeah, that's fine. I'm gonna leave. I already got that one. And I'm the teacher. It doesn't keep track of any of mine. Is there anything else? Oh, I didn't look at that one yet. Let's take a look at that. And we did one like that in class. Okay. So we're gonna just look at multiple derivatives of. Not the tangent. That one's kind of messy. Let's do the sine.
It just loops.
So it loops. It's kind of cool. F of x equals the sine of x. So what I want to do is I want f prime of x. I want f double prime of x, second derivative. I want f triple prime, third derivative. And after that, you can do things like f parentheses 4. That means get the fourth derivative of x. F parentheses 5. That means find the fifth derivative of x. But if you just put a 5 there without the parentheses, it kind of means the fifth power, so we don't want to confuse it. Anyway, start calculating. Let's see, what's the derivative? You can help me. What's the derivative of the sine of x?
Cosine.
What's the derivative of the cosine?
Negative sine.
And the derivative of the negative sine?
Sine.
Cosine.
Negative cosine, because the derivative of sine is cosine, negative
Yeah.
just hangs out. Derivative of the cosine is negative sine, so we already have a negative. So the derivative of negative cosine is just sine of x, and we're now back where we started.
Every third, every.
4, it goes through a cycle of 4 derivatives, yeah, that's what happens. So if somebody says, I need to know the 80th derivative of the sine of x, I would say, yeah, it's just the sine of x, because 4 goes into 80 with no remainder.
What's this on the test?
What's that?
Is that gonna be on the test?
Maybe. I actually didn't put it on the draft test, so it probably won't end up on.
I mean, it's an easy question. Put it on there. I want it on there.
I like.
So what if I said, what is the 81st derivative of the sine of x?
Cosine of
It would be just the cosine of x, because it's a multiple of 4 plus 1, and this is plus 1 derivative. Yeah. Not too bad, huh? Pretty cool. Yeah, it's kind of like powers of I. Oh my gosh, I is like the sine. Weird. Is there some hidden truth behind that? Wait until Calc 3 for that one.
Oh, no.
Hold you in suspense for the sequel of the sequel. All right, next we're moving on to the chain rule. So this is section 3.6. So the chain rule is where you have composition of functions to deal with. And I'm going to just pretty much use the same argument I used the other day, which is a little different than the proof the book gives, but it's similar. So an example of this would be, suppose I had the function letter, I'm going to use F and G. Let's call it S of x. And S of x is the sine of x squared. So here I have a function within a function. So I would say this is f of g of x. So we have this outer function and we have this inner function. In this case, my f of x is the sine of x, and my g of x is x squared. There's another kind of notation you've probably seen before. F O G of x means the same thing. Outer function comes first, inner function comes second. And that's not really an O, it's a little circle up in the middle there. Looks like fog, but it's not.
I don't like it.
It's like,
Yeah, so I do not like that notation. I will not use that notation. I don't think I sent any problems where it pops up. But if it does, my apologies. So anyway, we're going to play with this idea today. And I'm going to use the differential form of the derivative. So just a reminder about what that means. So if we take the derivative of a function like the sine of x, we know that's cosine of x. So that's the standard notation. The differential form of that is the derivative of the sine of x equals the cosine of x times this thing called dx. So we're actually treating the d and the dx as these quantities we can play with, as opposed to like just a process of what it means to do the derivative. So when we first encountered calculus together, this group of symbols right there said take the limit of the difference quotient, right? But we're moving beyond the limit of the difference quotient with these other ideas, and it turns out we can treat the numerator and the denominator as separate mathematical objects and play with them. And that just gives me some power to do things that I couldn't easily do without them. And this is going to come in handy in Calc 2. It's going to come in handy in a class you'll take in the future, maybe called differential equations. Anybody going in as like some engineering type field? I'm sure I've asked this before. Few of you? Okay. Let's see what other fields might require differential equations. Math teacher, yeah, that's another one. The differential version of it's going to come in handy in a bunch of different future math areas. So anyway, it's just a different way to write it. That's it for now. So coming back to my function, I had the sine of x squared, and I was calling x squared g of x, so then I'm just going to rewrite this as the sine of, and I'm just going to call it g for now. So then with this, I can do something like, since I'm saying g is my variable, I could take the derivative with respect to g, because you can use any variable you want for derivatives. There's nothing special about x. So, well, no problem. Derivative of sine is cosine, and the variable happens to be g, and boom, done. And then I could choose to put that in differential form if I want. So if I rewrite it in differential form, it looks almost exactly the same. I just get this little multiple derivative of g, d of g hanging out there. Now, we can then use our special information. G isn't just a variable, right? It's a function. So now I can consider, well, what is dg? So age, color. So we're at this point here, derivative of the sine of g is cosine of g dg, but g really equals g of x, and g of x is really x squared. So what is dg for us? Almost.
2x.
Almost.
2x.
Square.
Dx. The dx has got to be somewhere. Either it's going to go in the bottom on this side, or it's going to go on the multiple of that side. But when we're taking derivatives, the derivative of the variable has to be in there somewhere. And so if we use the differential form, it looks like that. Right? Other form is dx dg equals. Okay. Putting all this together, I get that the derivative of the sine of, what's g really?
X squared.
It's really x squared. So if I plug that in there, on the other side, I get the cosine of, what is g really?
X squared.
X squared. And then my dg is 2x dx. Taking that out of differential form, doesn't look much different. So I just want to point out some important things about this. It turns out this procedure works all the time, no matter what the functions are. I did it yesterday with just a 2x. Today I did it with an x squared. I can pick any function I want, repeat the same procedure. I'm going to get a similar thing out. The question is, what is significant about the output here? Well, it's kind of like the product rule. In the product rule, we take the derivative of one function, leave the other alone. Then we add on to that with the derivative of the other function. In this case, the way it happens is you take the derivative of the outer function and leave the inner function alone for a moment. Then part two is to say, now take the derivative of the inner function and multiply by it. Okay? So I get this chain of derivatives. They just get multiplied together. The trick to it is just figuring out, what is my outer function? What is my inner function? Once you've identified that, it's not too bad. Okay? So in general symbols, here's what it looks like. If you try to take the derivative of a composition of functions, f of g of x, then you're going to get the derivative of the outer function, but leave the inner one alone for a moment, times the derivative of the inner one. So if it was a product, the product rule says add the chain of derivatives together. If it's a composition, you end up multiplying the chain of derivatives together. But it's a pretty similar idea. They're very much related. So the big thing in my mind that helped me survive this is I have an outer function and I have an inner function. And bottom line, the answer is just outer prime times inner prime. But that involves just saying, this is my outer function, that is my inner function. And that's the way we'll approach it. We'll look at a composition of functions, we'll say, okay, here's the outer, here's the inner, boom, we'll get an answer. So let's go for it. So that's what's called the chain rule. Now, and I think the hardest part of it is identifying the outer and the inner and keeping this straight, that you take the outer derivative, leave the inner alone, then multiply by the derivative of the outer. So it's not too bad, it's just a process we get used to. Let's do it. New function. How about f of x equals x squared plus 3x plus 5 raised to the power 27. So, without the chain rule, we would be forced to multiply that sucker by itself 27 times. No, you can't make me do that. Turns out there's lots of computer programs online that'll do it for you. You just type that in and it'll say, hey. That would be nuts. It would have a lot of terms, right? I started with 3 terms, and I'm going to get many more than that. So we have the chain rule. So here it's just a matter of identifying what is the outer function and what is the inner function. So let's start with what's the inner function.
X squared plus 3x.
Yeah, x squared plus 3x plus 5. What is the outer function then?
27.
It's just the power 27. So write it like that. Parentheses to the 27.
What's inside?
All the other.
Who cares for now? We're just going to leave it blank for now. But we have to clearly in our mind say this part of it is the outer and this part of it is the inner. So I have to separate them for a moment. Now the derivative. F prime of x. What's the derivative of the outer function? Well, it would just be 27 times parentheses to the 26th. What ought to go inside the parentheses?
That x squared plus.
The original function has to go in there. Yeah, it's got to be the original x squared plus 3x plus 5. So like the product rule, I got to leave the other function alone at first. Now, what should I do next?
Times it by the derivative.
Yeah, times the derivative of the inner, which is just
2x plus 3.
2x plus 3. Not much I can do with that. I'm just not going to take the 26th power. You can't just slide that inside. You got to take that thing times itself, times itself, times itself, times itself. 26 copies of it. Right? So, we're done. It's a good way to finish a hard math problem or a proof. You just at the end, go boom, done. All right, not too bad, right?
Right.
Yeah.
Can we do one on the assignment?
Do you have one in mind?
No.
Oh, no. Thank you for asking. All right, let's try g of x equals 2 over 3x plus 5. Oops. Now, you may look at that and say, oh, this is the quotient rule. But I could rewrite this function as 2 times 3x plus 5 to the power
Of -1.
-1. Now, I can use the chain rule instead. Now, they're both hard, but once you get used to the chain rule, I think you're going to find it slightly easier. So to find g prime here, the 2 is just chilling out. It's a multiple. Multiples just hang out as multiples. Then I just say, okay, what's my outer function and what's my inner? So I'm going to do outer in red. Oops, red highlighter. Which one's the outer?
The -1.
The -1 power is the outer, and the inner
3x plus 5.
is just 3x plus 5. Yeah. So once we have that, we should be able to go on and take derivatives. So red. The outer function's derivative is
-1.
-1 times parentheses to the
-2.
-2. Chain rule says whatever was inside, leave it inside for now. So that's just going to stay 3x plus 5. Then the chain rule says, now tell me about the inner function. Its derivative is?
3.
Its derivative is 3.
-2.
So cleaning that up just a little bit, the -2 I can take to the denominator, and the numerator is going to be a what, -6?
Yeah.
Over 3x plus 5
Squared.
squared. Weird little artifact there. That wasn't too bad.
That's way easier than the quotient rule.
Let's double check that by actually using the quotient rule. So,
Gary, come on.
because sometimes you just stuck using the quotient rule. So we're going to do it just for fun. All right. What did I have there? 2 over. Okay. 2 over 3x plus 5. All right. So we got low d high which would be 3x plus 5 times 0 minus high d low all over low squared.
I guess it's not, I don't know.
In this case, it wasn't too much different. A little bit more work here. So I get negative 6 over 3x plus 5 squared. Yeah, so not too bad.
Like that uses more ink than the other one did.
It used a little bit more ink, yep. Yeah. The other one, I don't know, this used a lot of brain power because I had to think about the low d high, less high d low. This one I had to use some brain power, oops, wrong way, and think what's the outer, what's the inner. Okay. I'm not sure which is less brain power, and this slide is in the wrong spot. Where does that go? Back in the beginning somewhere. Later. Ooh, it didn't move. All right, let's try that again. Sorry about that. I think I put that right here. All right, let's do another one. Ooh, I got an extra screen. How about r of x equals the square root of 1 minus x squared?
So,
Can we rewrite it with a half power exponent?
Absolutely, that's an excellent first step.
Good idea. Let's do some.
Yeah, so, sometimes derivatives stick in your head. Like in my head, a derivative that's stuck is if I take the derivative of the square root of x, I remember getting 1 over twice the square root of x. So if you remember that, then you don't need to switch it. But if you like the power rule better, use the power rule. But we had done that one enough in the previous homework that I was thinking some people might remember it. Anybody remember that, by the way?
Yeah, I remember it.
I
I
get it.
like that better.
Okay, cool. So here, let's take a minute, because this is a bit more complicated, to identify the outer function and the inner. Okay, so what's the outer?
It's the square.
It's the square root or the power 1/2. Choose your version. And the inner,
1 minus
1 minus x squared. And that's kind of complicated, but we can treat it as a single function. It's not really a composition, although it could be if we wanted. All right, now we go for the derivative. So r prime of x is the derivative of the outer
1/2 times whatever to
1
the
minus
negative 1/2
Yeah.
power.
right? Because we got to drop the power by law and we get a negative 1/2. So now I'm going to slap back in my inner function. And now I have to multiply by the derivative of the inner,
Negative 2x.
negative 2x. And please pause to clean this up. So let's see, we have a 1/2 times a negative 2. I like that. And then maybe I could take that negative, put it in the bottom.
Yeah.
Okay. So then I'm going to get an x over 1 minus x squared to the power 1/2.
Yeah.
If you like square roots, then it's x over the square root.
Wait, it's negative x over.
Oh,
Because
negative
it's
x,
times
yes,
the
yes.
negative 2.
Positive times a negative is a negative. Negative x over. Yep. So I just want to show you something cute about this derivative.
Cute?
Yes.
What's that?
Check this out. Have you seen the equation x squared plus y squared equals 1?
Yes.
What? It's the unit circle, right? Okay, cool. If you solve that for y, what do you get?
square root
1
of
over
1
x
minus.
squared.
Wait,
One.
the
Square root of
square root of
square
1
root.
minus x squared.
Yeah, you get y is plus or minus the square root of 1 minus x squared, which we have part of that right there. So what must r be the graph of?
A half.
The upper half of the unit circle. Yeah, it's the upper half of the unit circle. Okay, that's kind of cool. So we just found that if we take the derivative of this thing, y prime was equal to the opposite of x over the square root of 1 minus x squared. Now the minus would just be the bottom half, so we're just going to ignore the bottom half for a minute. Okay? This has some significance. What is that?
I have a
So
circle.
I have the.
It's y.
Oh my
Okay?
god. So,
So where am I going with this? It's some cool geometry. So y prime is equal to negative x over y. Okay? And what does y prime tell us about a function? Tells us a few different things. It's the slope function, right? It
Yeah.
tells us the slope at a point. So this says on the unit circle, the slope at any point is the opposite of x over y. All right, let's draw a picture and see what that looks like.
We didn't know this for the
So
test.
if we need a tangent line of a circle.
This is a connection to all kinds of math you've seen before that's beautiful.
So if we need a tangent line.
Is it going to be on the
of
test? How about a maybe? Does that make it more interesting?
Sure, yes, absolutely.
So there's the semicircle. If I pick some point here, right there, that's the point. This is x and that's y, right?
Mhm.
So here I have y is a little bit bigger than x at that point right there. So the slope here, something like, there's my tangent line, and they're perpendicular on a circle. I don't know if you remember that from trigonometry.
Sure.
Okay. What's the slope of that line right there? That radius.
R.
Y over x,
Alright.
right?
And then,
Isn't that what this says, y over x?
yeah.
What's the relationship between a line and a perpendicular line in terms of slope? Negative reciprocal. So what does the slope of the red line have to be?
Negative x.
Isn't that cute?
Wait, is
Is
it?
that a beautiful connection?
Does that?
We did it without calculus. There's some problems you can solve without calculus.
So does mean we need the tangent line of any circle?
The tangent line
On a
of a
point
point on any circle is going to be the ratio of the distance. Now, if it's somewhere else besides the origin, that's more complicated, but not much. The bottom line is the reciprocal of that length over that length. I mean, sorry, it's the fraction of this length over that length. So bottom line is take the slope of the radius and negative flip it.
That's my
And that's the, I thought that's pretty cool
We
geometry.
can cheat and
It's
do
adorable,
geometry.
Gary.
It is. Thank you very much for appreciating that.
You're welcome.
All right, let's pick one from the homework for fun. 3, 6. There's a whole bunch of videos. This is a really cute video right there. I highly recommend it. The graphical approach to the chain rule. I should have named it a really cute video of the chain rule. Check it out. It's really good. I'm not going to watch it in class because you can watch it at home.
We have 7 minutes.
All right, we got lots of time. Let's jump in the middle. Ooh, that's a lovely one right there.
Does that mean we have to use the quotient rule?
And the chain rule. Yes. This is a good combination. So, screen snip that thing.
This homework that would be fun.
It is. That's why I have 2 days on it. Oops. There's my pointer thingy.
I think your definition of fun is a little bit different than this.
Yeah, I like biking up hills for fun.
I
So
think his definition of cute is also.
I also like. I also vacuum for fun. So yes, my definition of fun is a
Are you
little-
one of those people?
I'm one of
Wow.
those people.
A full-fledged adult.
Okay, so we have to identify outer and inner. So outer,
It's something to the 8.
something to the 8, beautiful. And inner,
Is x plus 4 over x plus 3.
okay,
You're equal.
equal. Yeah, so the hard part here is the derivative of the inner. That's gonna be the tough part.
Can we do
We-
it first?
We could totally do it first.
Let's do it first.
Okay, so the derivative, so let's find d inner dx, oops, extra line there. So let's see,
inner.
low d high,
Sorry, I'm laughing at the fact that it's dinner. This is dinner.
dinner, oh man, it's lunchtime soon too. Minus high d low, use parentheses, practice safe math,
1.
times 1. Over low squared, low. All right, so that really is just going to be a multiple of the derivative of the outer, right?
Sure.
I'm just going to slide that sucker over here so I can squeeze in a multiple. So times, what's the derivative of the outer?
8
8
times all that to the 7th
to the 7th. And what goes in the parentheses?
X plus 4,
X
X
plus
plus
4.
3.
Yeah, just real simple. X plus 4 over X plus 3. And we're done.
And the X plus
Wow, we should
Yeah,
probably
clean
clean
up
it up.
that second part.
Yeah, okay, we'll clean it up. So, 1 times X plus 3 is X plus 3, but the minus has to be distributed. So minus X minus 4.
So aren't you just left with -1?
Just -1, yeah. So now I have 8 times X plus 4 over X plus 3 to the 7th times -1 over X plus 3 squared.
Yeah.
Yeah.
Yes.
Absolutely.
Can we take it one step
Don't
further?
even go there, dude. Yes.
We can take it one step further. It turns out, although you can't distribute a power over a sum, you can distribute a power over a quotient.
Okay.
Because then I'll have a whole bunch of X plus 3s in the denominator.
Uh-huh.
And you can cancel 2 of them.
Yeah, so I'm going to say this is -1. No, nothing cancels here.
Oh.
Because multiplication means multiply across the top, multiply across the bottom. Nothing's going to cancel. But I'm going to say this is going to be -8 times X plus 4 to the power 7 divided by X plus 3 to the power
Say
14.
almost 9. So here's going to be the power 7, and then there's 2 more of them.
Totally nice.
Power means multiply together, so that means there'll be 9 of them altogether.
Oh, so you don't multiply the powers, you just add them.
You add the powers,
correct.
Yeah.
Oh, I
That's
can't.
what I want.
Yeah. Not too
I
bad.
just went against everything.
Will this kind of thing always clean up like this kind of thing? The answer is yes.
Yes.
Because X plus 3 is going to be in the bottom here, and it's going to be in the bottom there.
Oh, okay.
So that's always going to happen with something like this.
So could it in turn be X plus 3, like raised to -1? Or am I not?
You could take that to the -9th
No,
instead.
like, before, because we did the quotient rule, but could you take, of course, it was awful.
Oh, could you write this up here as something like X plus 4 to the 8th times X plus 3 to the -8th?
Yeah.
And then use the product rule?
Yeah.
Yes, you could. That would work too. Yeah.
Why do there have to be so many different ways to do one problem?
Anytime a problem is complicated, there's always going to be many ways. That goes all the way back to arithmetic. All right, let's do another one. Let's see, there was a really cute one in here. 13? No, I'll let you struggle with that one.
Oh,
thanks.
thanks.
We'll bring it back tomorrow.
Oh, this is it right here, I think.
Here.
It's a trig function.
Ooh, and here we have a function of a function of a function.
Can you do it
You
in
have
2
to-
minutes?
Ooh, yeah, totally.
You have to chain roll the chain roll.
We chain roll the chain rule, which is just like chain ruling the product rule. Oh, that doesn't make sense. That's just like having more than 2 things multiplied. You just add another derivative in the chain.
Okay.
So if you have a function within a function within a function, like an outer, a middle, and an inner,
That's the G times the F.
it'll
times-
just be the derivative of the outer times the derivative of the middle times the derivative of the inner.
So it's the F prime plus.
F
F
G.
prime.
So if you take the derivative of f
F
of
G
g of h
So many-
prime, then that's going to be f prime times g prime times h prime.
You said that weirdly.
And then what goes inside these? Well, f had a g of h, so g of h goes in here.
And G had an H.
And g had an h, so the h goes in here.
And H
And
had an
h
X.
just had an x. Yeah, so basically you just find whatever the outer is, take its derivative, put back whatever it had.
So-
Identify the middle, take its derivative, put back in whatever it had. Okay. So let's just identify outer, middle, and inner here. So outer,
Is the
middle, inner. All right, outer, we could call that 3 cosine. Sure. Inner or middle,
Cosine.
just the other cosine. And inner is x to the 5th. Yeah, so we just need to take these derivatives and chain them, and then put stuff back in. So the derivative here, f prime of x,
Is.
derivative of 3 cosine is -3 sine
Yeah.
of stuff.
Stuff.
Times,
Negative
middle.
sine.
parentheses, negative sine of stuff
Times 5x.
times
5x to
5x
the 4th.
to the 4th. Right. So then I go back in and fill, what did the outer function have in it?
Cosine of x to the 5th
Yeah,
power.
so that's what goes here, cosine of x to the 5th. What did the middle have in it?
X to the 5th.
Yeah, that was just an x to the 5th, and I'm done.
Fantastic.
Could clean this up a little tiny bit. Negative times a negative, 3 times 5. So I guess I would say this is 15 x to the 4th times the sine of the cosine of x to the 5th times the sine of x to the 5th.
I think we're gonna put a negative on
Yeah.
that.
The negative side.
X on the second sign.
It's a negative.
I have a negative times a negative.
Oh, okay. So
Oh.
you just essentially factored out a -1.
Yeah.
Off it.
Yeah.
Okay.
Yeah, so more of these tomorrow. We got a couple days on the chain rule. Have fun, we'll do more.
Time for fun with math is over.
Yes, it is today.
Headache can stabilize to a headache.